Circulation. Let's compute the circulation here. Gamma is integration of u dot dx, right? Let's do that. Let's take our cylinder as a closed curve. So it's integration from 0 to 2 pi over the cylinder. The dx will be tangential, r d theta, right? And the velocity along the circle is what component? The tangential component. Very good. So this is along the cylinder. This is A of the cylinder, and this guy already got it. It's negative 2u infinity sine theta. So let's get negative 2u infinity A outside, and we're integrating from 0 to 2 pi sine theta d theta. You get here negative cosine theta between 0 and 2 pi, which you get 0. No net circulation. And we know from the beginning, before doing anything, if no net circulation, it's no net lift, right? So in order, this is the potential flow. So the potential flow around the cylinder will not give you any lift at all. Why? We'll talk about that later on, okay? When we get to the physics, you should now expect why a little bit. But later on we will talk about it in detail, okay? Potential flow cannot give you any lift, so you have to add it yourself. Here is the point. I will add gamma here, of course, of unknown strength. And remember that, yes, it's unknown strength, and it's very important because tell me how much gamma you will add here, I will immediately give you how much lift you will generate, right? So this is a very crucial piece of information. It's a very crucial part of your analysis. We're going to add gamma to be lifting, but it's actually, we're kind of cheating. Why? Because you're interested in the lift. This analysis doesn't provide you any lift at all unless you add gamma, and it's only this gamma that will generate you the lift. So if your colleague decide to add twice the gamma, you will get twice the lift. So it's completely arbitrary. You see what I'm saying? This is really kind of cheating. If you want to say, potential flow cannot alone give you any lift. Period. You have to get it yourself. So we add a circulation, and we know a priori that depending on that circulation, I will get that much lift. Okay? But let's add the circulation and see what the circulation does to our flow field. Okay? Any question up to this point, please? Any question? If you have any question, stop me, please. Any question? Okay, so let's add a circulation. So lifting cylinder. What's that? This is uniform flow plus a doublet. This is the cylinder only plus vortex, point vortex. Okay? At the center. Okay? So F is, you can get F immediately. It's U infinity times Z. This is the uniform flow plus the second part is K over 2 pi Z plus the third part is gamma over 2 pi I ln Z, and I added a negative vortex in that sense. Okay, so this is why I put a negative. So first of all, if you add the vortex, do you expect, remember here, so uniform flow plus doublet, this is a circular cylinder. If you're adding a third element, you might get a different body, right? Do you expect that we will maintain the cylinder as a body or not?
Sure.
Why? Yes, we will maintain the cylinder. Any reason why?
The radial velocity doesn't change.
Exactly, because this guy induces only tangential velocity, so it will accelerate and decelerate flow, tangential flow here, but will not add any radial component. In other words, it will not stop the cylinder from being a straight line. The flow is still completely tangential to the cylinder. There is no radial component added. And this is why, this is the issue, that you can add maybe much circulation here. You can add much circulation without disturbing the only boundary condition that we need to satisfy in potential flow. What's that? the no penetration boundary condition is the flow is tangential. The flow will always be tangential irrespective of the strength of the circulation area. And unfortunately, you keep adding circulation, you get more lift. Okay? So this is a problem. This is a critical problem that we need to reconcile. Anyway, so this is the flow field. Of course, it's the same cylinder, so we have the cylinder is streamlined. We have the same radius, k over 2 pi u infinity squared here. But here is the issue. So, this is the cylinder from before. These are the 2 points. These were the stagnation points for no circulation. Stagnation at gamma is 0. If you add circulation, the stagnation points actually change. Here is still on the body, on the same R, but here is without, I will not go and derive them. You can do it exactly the same way I did it in the first example. Sine theta stagnation, this is sine, okay, is gamma over 4 pi u infinity, and it's negative. Where is that? Sine is negative where? Sine is negative where? So this is the effect of circulation here, gamma. So look at this. The velocity field were symmetric. Okay? Adding gamma will accelerate the flow on the upper surface and decelerate the flow on the lower surface. Accelerate the flow here, meaning lower pressure, here, meaning higher pressure, so you get lift. So this is how we get the lift. Okay? Now, because the flow was symmetric, it comes exactly here and stops. But you accelerate the flow on this surface and decelerate the flow on that surface. Then where the stagnation point will go? Somewhere here, right? Exactly. So these are, so this is why the sign is negative. The sign is negative in these quadrants, third and fourth. Okay? These are the two new stagnation points, and you have the location here. It depends on gamma. So yeah, gamma will add you some lift. Unfortunately, because you know, it depends. It really depends on how much gamma you add. You will get how much lift. But it controls the location of the stagnation point. This is very important. Any questions so far? Any question? Please. Okay. I guess we have some time, right? Yeah, we have some time. So let's see what else do we need to cover today. Oh yeah, we can. Oh, wow. Still some stuff. Actually, we don't have time to cover all these. Okay, let's go. Keep this in mind because this is very important, okay? Let's see. What about if I have more complicated shapes? What can I do? You managed to solve the flow around the circular cylinder. Well, why not turn everything into a circular cylinder? The answer is conformal mapping. So you need the flow around this funky shape. Well, I can solve the flow around the circular cylinder and just map it. So this is your real domain, x plus iy, z here. This is your fictitious domain, large x plus I, large y, xc. And I have a function, z is a function of xc that maps this domain into that domain. Well, that's fine, but can any function work? Of course not. For example, I mean this function, if this function is not one-to-one, for example, if this function is not one-to-one, Will it create a problem? What do you mean by not one-to-one? I mean that something like x squared, c squared, just c squared. So you have a point here, it maps over there. You have another point here, it maps to the same point. It's like the, the 3 and negative 3 both maps to 9, right? 3 squared and negative 3 squared. So this function is not one-to-one. It maps 2 points, so even more to the same point. That's okay. Now I want to go the other way around. If I want the flow field here, I want the flow field at this point, I should go and look at the corresponding point, but it corresponds to the different points. This is a problem, right? So obviously not every function will work here, it has to be one-to-one. Okay? It has to be also differentiable, this function in the complex domain. Why? Because we will see that the velocities will be magnified by exactly the derivative. So if the derivative doesn't exist, you will not be able to transfer velocities. So these turn out to be the two conditions for a conformal mapping, is that differentiable and one-to-one. This means the function is conformal. Okay, conformal mapping. And then you get the following, that it actually preserves angles. This is great. If you have a flow with the angle of attack, it's the same angle of attack over there. Okay? So, this is my flow field that I'm very interested in solving as an aeronautical engineer. X and I, Y, Z. I want to solve the flow around the flat plate. With an angle of attack, U infinity, alpha, okay? C over 2, negative C over 2. This is the flow field that I want to solve. Now we just learned how to solve the flow, this flow field. The same alpha. Luckily, the conformal mapping preserves angles. And this guy is A. And I need to map Z is function of Z. Okay? This is, you all know guys that this is Joukowsky transformation. Z is zeta over xc plus a squared over xc, where this is 2a. This transformation exactly does the job. So next time we know this, we'll just state it, get the flow around flat plate. Now we managed to know the flow around the flat plate, which means we managed to get the lift over flat plate subject to a very essential piece of information, the circulation. You gave me your circulation, I gave you your lift, which you already know from the beginning, but now we know more information. What do we know more? Beyond the lift, I know the flow field. Okay? I know the flow field, I know the velocity everywhere, I know how the streamlines look like, but still the lift is problematic. You have to give me the amount of circulation that needs to be generated. Okay? And it would be great if you can relate the amount of circulation to that flow field. It would be great if we can do that. Any question about that? Okay, see you next Monday.